so today we're going to cover 1.1, 1.2, and chapter 1. And the things in this chapter, here's the things we're going to do. Now, you don't necessarily need to write down every single word that I put on the screen. For one reason, it'll be online. So, you know, if you need to review it, it'll be sitting in D2L for you. Or you might just want to write down a couple of keywords or whatever. You don't have to write down everything, every single word. So what we're going to do is we're going to review the number system. And notice the word review is at the beginning of all of these. So all of this should be things that you've had, well, they are things you've been taught before. Hopefully you've learned them as well as being taught them. So we're going to review the number system. We're going to review properties of addition and multiplication. We're going to review what it means to be a number line order. And we're going to review the order of operations. Okay. Okay, the number system. Number systems evolved, and I'm not saying man evolved, but number systems evolved as man became more and more refined in explaining how this world operates. Let me explain it in much simpler terms. If you have a younger brother or sister, like preschool, one of the first things that a preschool kid is supposed to accomplish is counting. And so when they start counting, when you're little, have you ever noticed this? They go, and my granddaughters do this. They go 1, 2, 3, 4, 5, 6, 7. I have 7 things. And really they have 4, but they don't have that one-to-one. So they call it one-to-one correspondence yet. And so they have to be taught. 1, stop. 2, stop. 3, 4. 4 things. And that's the way, when we first started using numbers, when man first started using numbers, that's all they did was count things. I have 1, 2, 3 cows. You only have 1, 2, ha ha. Okay, so the counting numbers, the number system, the very first one, the easiest, the simplest, the most itty bitty one is what preschoolers use, and they're called natural numbers. And you start with 1, 2, 3. Basically, you count your fingers. These are also, it's natural because that's where you naturally start counting, is at 1. So it's 1, 2, 3 on up. Some people, though, because we do count with the natural numbers, they're also called counting numbers. So natural numbers and counting numbers are the exact same thing. Okay. All right. So then life went on fine, just counting things, until one day somebody said, well, what if you take the whole number 2, or excuse me, the natural number 2, and you take away 2? What happens? Oh, we don't have anything for this. There's nothing. So man had to say, well, we got to come up with something. So they came up with the 0. And when you stick a 0 in front of all your numbers, those are considered the whole numbers. Whole numbers. This is the way I remember that. Whole has a O right there, like the O that you added in front of all your counting numbers. I always come up with goofy ways to remember things. So whole numbers is when you put a 0 in front. And the first person, mathematical history is fascinating. The first person that came up with a 0 in our history of mankind, they thought he was crazy. How do you write down something for nothing? If there's nothing there, why do you need something for it? Why do you need to write down something? There's nothing. And he was kind of ostracized in society, but finally they realized, okay, he's smarter than we think. Then somebody else questioned this. They said, well, what happens if I have 3 cows and I take away 4 cows? What happens? Well, it's not 1. It's not any of the numbers we know of. So what did man have to come up with? What would be the next thing they have to come up with? Yeah, negatives, right? Because this is a -1. And right now, in the whole number system, there are no negative numbers. So the next thing man had to come up with was, we call them integers, but basically we had added the whole left-hand side of the number line. Okay, So, all right, so we counted first, starting with 1. Then we added the 0, which made whole numbers. Then we added the negative side of the number line, which now we have integers. What do you think might be next? What would be a question? What if you were to take the integer 2 and divide by the integer 3? Do you have an answer in our list of numbers? We do not. So what did we have to come up with? Yep. The F word, what is it? Talk to me. Fractions. Yes. We had to come up with fractions. Okay, so we added fractions, and a fraction is called a rational number. Rational numbers are fractions. And basically, rational numbers are in the form of P over Q, some number divided by some number. So you have an integer over an integer, or an integer over a natural number. Wait a minute. Integer, whoa, integer, that's not a good color. Hang on a second. Let me get me a white will best of this color. If you think about a fraction, I have a number on top, I have something on top over something on bottom, right? I'm just going to use stars. This top number can be any integer, which means it can be positive or negative. This bottom number can only be natural numbers. Why can the bottom number not be your denominator? Why can it not be whole numbers? What do whole numbers have in them? A 0. And can you have a 0 as a denominator? Watch this. What is 0 in the numerator? What's 0 over 1? What's that value? 0, because 0 times 1 is 0. What's 0 over 3? Talk to me. 0, because 0 times 3 is 0. What is 2 over 0? Is there anything times 0 that's going to give me 2? Nothing. Nothing times 0 is going to give me 2. Nothing. Sad face. Nothing there. That's why when you get a 0 on the bottom, it's undefined. So I could not put a whole number on the bottom, because a whole number, I could put a 0 on the bottom, and that'd be a problem. So I can only put natural numbers on the bottom. Okay. All right, so then at some point, someone told us that there were square roots, and as long as it was a square root of 4, that wasn't a problem, because we could get a 2, and that's in our system. But what if we have the square root of 2? Well, I'm going to pause for a minute. Well, I'm going to pause for a minute and let you get out your calculators. So put the square root of 2 in your calculator and tell me what you get. 1 point, give me some numbers. 4, 1, 4, 2, 1, 3, 5. How far can I go? Does it ever stop? Does not stop. It stops on your calculator because your calculator runs out of room on the display screen. But this number repeats forever and ever. Never goes away. Just like pi. Do you remember the value of pi? 3.14, and then it goes on and on forever and ever and ever and ever. What's that?
Yeah, I knew like a few of the numbers.
Yeah, there's always YouTubes about kids that memorize the first 100, out to the 100 places past. Crazy. But the point is, these are called repeating numbers. They never end. Well, we certainly didn't have that when we just had rational numbers. So we had to invent another kind of number, and that's called irrational numbers. So irrational means not rational, means weird. This is weird that a number would never end. That just seems weird. Okay. So when you put all of those numbers I just told you, all of those numbers together, they make up the set of real numbers. Every number that I just told you about. The integers, the whole numbers, the rational numbers, the irrational numbers, all of those are considered real numbers. Now you might be thinking, well, of course they're real. What else is there? Well, believe it or not, there is a whole number system of imaginary numbers. And you will learn about imaginary numbers. I can't remember if it's this semester or next semester. I can't remember exactly where it is in our book. But there is a whole another system of imaginary numbers that you don't even know exists. In the same way that when you were little, and the first time you heard about negative numbers, it kind of blew your mind. It was like, what? There's a whole nother, you could go to the left forever? You don't remember that, but probably in, when would you get that? 3rd grade, 4th grade when you start doing negatives? 1st grade? I don't know when you start negatives, but it probably blew your mind. So let's put all of that together in a chart here, so you can see how these all fit together. Okay? Okay. All of these little guys, oh, I need to back up a second. Gosh, it's been too long. I can't remember how to get back. All right, so what we're going to do is we're going to, each of these things move. Okay? So let's see which of these blanks that we go in. So we're going to start with, am I recording? Yes. Okay. We're going to start with the 2 big sets. Notice, see the 2 biggest rectangles? The biggest rectangle that you know of is real numbers. Those are the ones that you've been doing all your life. And will until you learn about imaginary numbers. So the other numbers in the universe are called imaginary. Now, everything we just talked about is all on this real number side. So let's start in the middle of this circle. What was the very basic number we started with? What did we call those when we in preschool? Good, the natural numbers. So the natural numbers was where we started. And then to the natural numbers, what did we add? A 0, which was the whole numbers. So that'd be the next biggest circle. And then to the whole numbers, then we went to the left of the number line. Not yet. Let's do, yeah, integers were next, because remember, first we need to get like -1, -2, so on. And then after that, out of the integers, we made fractions, and those are called rational numbers. So all of these are rational numbers, and so what do you think will go over here? The only thing left, irrational numbers. These are numbers that repeat forever. So you can see why the majority of the time in life, you just work out of this one little half of a rectangle. These 2 are kind of reserved, except for, did you know that your cell phone is totally run by imaginary numbers? This world over here that you don't know about yet, that's what runs a cell phone. So it's not that imaginary numbers have no significance, it's just that in where you are now educationally, we just focus over here. And we'll get more into this, and if it, somewhere in Algebra 2, you'll get a little bit into this one. Okay. All right. This you've done before, graphing on a number line. So let's say, well, you tell me, what do you think is the easiest way to graph on a number line?
Are you trying to get back out?
Yeah, well, I'm trying to get a pen again, because see, I don't have a pen. Go back to what?
Go back to, yeah.
That one. Oh, yeah. Comes back to me now. So what's the easiest way to put these on a number line? You remember? You might want to use a little tool that's in your hand. What would that be? Starts with a C. C-A-L. Come on, guys, talk to me. Calculator. Let's get your calculator. What is the square root of 3? Give me a value for square root of 3. Oh, I'm still in white. Give me a value for square root of 3. 1.7 something. Give me a value for 5 divided by 4. 1.25. All right, so now we've got to put both of those. So both of these are going to be in between here, right? What is right in the middle? What is that number? 1.5, 1.5. So therefore, 1.7 would be somewhere over here. So my square root of 3 would be about there on the number line. 1.25 would be to, oh, that would also be to the right of that, because no, to the left of that, because this is 1.5, that's 1.2. I'm even going to take this off a minute and make 1.2, so that's going to be somewhere over here. This would be my 5/4 right here. Okay, so converting them to decimals is usually the best way to get that done, and then it's really easy to compare the two. What if we have all this? We want to list these in increasing order. Increasing. So am I going to start with my lowest number or my highest number? Lowest. Right. All right, let's divide and conquer here. This one is already negative 0.2. So I've got a negative 0.2. This side over here, tell me what 7/10. Give me a fraction for that. What is 7/10 as a decimal? I'm sorry. 0.7. Okay. 0.7. Then we have a negative 1. This side over here, give me the square root of 7. What's the square root of 7? 2.6. And then I have a negative 4. All right, so now I'm comparing all decimals. So which one is the absolute smallest of all of those? Negative 4. So negative 4. And the next would be, would it negative 1? I've got a negative 4. I've got a negative 1. Beautiful. Then a negative 0.2, because that's going to be, it's still a negative, so that's going to be somewhere around here. Then I have left a 0.7 and a 2.6. What would come next? 0.7, and that's not quite a 1, so that's going to be maybe here. And then the 2.6, a little over 2.5. Okay, so again, putting it in all in decimals is the way to compare the best. Okay. Did we do that one yet? Nope. Okay, let me stop a minute. I'm going to pause and let you do this one on your own. So in your notes there, write these in increasing order. Increasing order. So again, we're starting at the left, at the lowest, going up to the highest. I'll give you a minute. All right, would everybody agree with that order there? Everybody good? Go? All right. Then let's move on. Let's talk about the properties of addition and subtraction. A couple things let me point out to you. First of all, the word properties. What the heck does that mean? I'm not talking about a piece of land. If I say the properties of math, or the properties of science, or the properties of gravity, what am I talking about? What do properties mean? What it looks like? I could say, what are your properties? And you could say, well, I have brown hair, brown eyes, I'm 58 years old, I have 2 legs, 10 fingers, whatever. You know, what are your properties? What are you made of? What do you like? What are the rules that you run your life by? Those kind of things. So, properties, there are, let's see, I think we have 5 of them here that we want to really emphasize today. But hang on, I want to do one at a time. And you do want to make a little chart of these. Go in and put, you know, a chart with 3 columns. In the first one, call it properties. Property. In the second one, we're going to talk about how that property works with addition. Third column, how that property works with multiplication. All right, so let's start with the first one. And it's closure. Closure. And you've had these a lot. You probably don't remember them because it's like we teach them and then we don't use them, but you do use them all the time. We just don't identify them very much. We don't use the words, but closure, if you have closure, let's say you move. say you move from one town to another. Before you leave your old town, you like to, like say you like to have closure. You like to go around and tell everybody bye. You want to make sure you go to the gym where you worked out, tell them bye. You want to tell everybody at school bye. You want to tell your friends in the neighborhood bye. Each of those experiences, you kind of close off the relationship because you know you're moving on to something else. Okay, it's a closure. Well, kind of in the same thing here. I'm not finding a very good parallel, but just so you know what the word closure means. If you add any real number plus any real number, you will always get another real number. There's no way you can add two real numbers and come up with an imaginary number, is basically what it's saying. And the same way when you multiply. If you multiply two real numbers together, your answer will always be a real number. You will not get an imaginary number. And that seems kind of silly. Seems kind of silly to have to state that. But that's what you do. That's called closure. And the next one is commutative. Notice this is not communitive with an N. It's not commutative, it's commutative. Now let's think about what the word commute means, because this does definitely go right along with the definition. You commute every day. You go from home to school, back to home, back to school, back to home, back to school, back to home, back to school. You're just basically switching places. Well, that's what happens here. The A plus B is the same as if you switch those places, B plus A. If you rearrange them, you're still going to get the same thing. If I have 3 plus 2 over here, and I rearrange them to be 2 plus 3, I'll get the exact same number on both sides. That's all that's saying. I can rearrange the order if I'm adding. Same with multiplication. If I'm multiplying two numbers and I rearrange them, if they commute into each other's space, it's fine. I'll still get the same thing. Because 3 times 2 is the very same thing as 2 times 3. Now, just out of curiosity, does this work for division? It doesn't, because 2 divided by 3 is not the same as 3 divided by 2. So it doesn't work for division. How about subtraction? Does it work for subtraction? That's right. Because 3 plus 4, excuse me, 3 minus, I'm doing subtraction on that. 3 minus 4 is not the same as 4 minus 3. Because, as you said, this is a negative 1, this is a positive 1. So it only works for addition and multiplication. All right, there's commutative. The next one is associative. Associative. And this root word is associate. This one definitely goes, the word goes with the definition. Who you associate with, I could say who you hang out with, who you run around with, who's your buddies, who you associate with. So notice in these problems, I've got A plus B plus C. On the other side, I have A plus B plus C. The order has not changed. What has changed is on the left-hand side, the A and the B associated or hung out together, and the C was kind of a third wheel. On the right-hand side, the A was the third wheel, and B plus C hung out together or associated together. See the difference? So it's not the order right now, it is the grouping, or who's buddying up with who. So same thing with multiplication. A times B times C, A times B times C. Order has not changed. What has changed, A and B are hanging out together. On the right-hand side, B and C are hanging out together. And that makes sense, because 2 plus 3 plus 4, let's say, equals 2 plus 3 plus 4. So on the first one, let's let these two guys hang out. The second one, let's let these two guys hang out. This would be 5 plus 4 is 9. This one would be 7 plus 2 is 9. So it really doesn't matter. And I could do the same for multiplication and see that it doesn't matter. Then we have the identity property. Identity property. Again, let's think about the word. Identity or identical. An identical twin, they look, how do they look? The same. So what happens with the identity property is you start off with a number, let's say 6. And if you add 0 to it, you'll end up with the identical same number. The number does not change. Started out as 6, ended up in a 6. Works the same for multiplication, except when you multiply, the element is 1. 6 times 1, anything times 1, and it gets you the very identical same thing you started off with. Okay? So identity is what you might think it is. You end up with the identical thing, same thing. Then the last one is the inverse property. The inverse. The inverse property gets a little more tricky than the others, but it's still not hard. You use it all the time. When you hear the word inverse, you think things like reverse or invert. So you're kind of undoing something or inside out or you kind of something like that. So that's what happens here. If you take any number and you add its opposite to it or kind of reverse it or invert it, you know, you end up with 0. So any number plus its opposite is going to give you 0. That's how it works in the addition column. In the multiplication column, what do you call, if I have the number 3 in relationship to 1/3, what do you call 1/3 in relation to 3? Do you remember that word? RE something? RE, there you go, reciprocal. So in multiplication says, if you take any number, you multiply by its reciprocal, or you kind of inverted it or reversed it or kind of inverted, however you know, you end up with a 1. So in addition, you add the opposite, you'll get a 0. In the multiplication, you multiply by the reciprocal and you get a 1. So those are all our properties. Oh, there's many more properties, but those are the ones we're going to focus on today. The last one is distributive, but you really know this one. And just write down distributive in this example. You know how to do this. The distributive property involves both multiplication and division, because if you have a problem like this, you know that you go 3 times 2 is 6, and then you do 3 times 6 is 18. Hold bloop, bloop. And you end up with what? 6, 4, 24. Distributive property is not hard to do at all, or identify. All right, so let's do some practicing here. Again, these will all move. Okay, so I'm going to call on different ones of you, and I want you to use these little signs and go move them next to whatever property is shown here. Okay, and these are going to take some thought. It's okay, we'll work together. Don't worry if you miss one. So I'm going to do the first one to show you what I mean. 5 plus -5 equals 0. So I'm adding a number to its opposite.
Inverse.
Very good. That's the inverse property. So I'm going to take this and move it. Actually, I'm just going to, yeah, just stick it right beside it. Okay. So for those at home, look and see if you got these answers. Commutative would have been at the very end. There we go. Okay. Y'all feel like you know that pretty good? Do we need to practice again, or are you good? Let's do this. This is what you need to move on. What is an exponent? Exponent, you know what an exponent is. What does it tell you to do? So if you have 3 to the 4th power. Excellent. Does not mean 3 times 4. It means 3 times itself 4 times, right? And of course we can do 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81, right? You know about that. You know about exponents. So when we do order of operations, do you remember PEMDAS or please excuse my dear Aunt Sally? You always do the parentheses first and go back and do exponents. And then you do multiplication and division from left to right. So sometimes you do multiplication and division, sometimes you do division and multiplication, depending on which comes first in the problem. So those two are together. And then the add or subtract again, you do whichever comes first in the problem. So, you know this, let's do this. 27 divided by 3 squared times 2 minus 3. What of those operations would I do first? 3 squared. So I'm just going to do one thing at a time. So I'm going to put 9 there. I'm going to bring everything else down exactly like it was up above. I'm not going to try to do more than one step at a time. Now I've got division, multiplication, and subtraction. Which one will I do next? I'll do the division. Even though down here the D comes before multiplication, but remember you do whichever the MD comes first. So 27 divided by 9 is 3. Bring everything else down. Now I have multiplication and subtraction. Of course, multiplication would come first. So I end up with 3. And if you don't do it in that order, you will not get the right answer. You'll get a whole different answer. Remember, groupings doesn't always mean a parenthesis. Sometimes it means brackets. These are called brackets. You know what these are called? I think they're braces. I think these are called braces. So they could have different kind of groupings bars. A grouping bar could also be a fraction bar. If you have a fraction bar, then you're going to do what's on top divided by the whole thing on the bottom. So I'd end up doing the 8 plus 4 first and then dividing by 3. What is the difference between negative 2 cubed and negative 2 cubed? Or is there a difference? This right here is this screen right here is what even my calculus and analysis kids mess up the most. This screen right here. What is the answer to this problem right here? What's the answer to that? Is it negative 8 or positive 8? It's a negative. This means the opposite of 2 cubed. Well, 2 cubed is 8, so the opposite of 8. This means negative 2 times negative 2 times negative 2, which is 8 with an odd number of negative signs, so it's also a negative 8. So actually, there's no difference between those two. However, look at this second one. Without a parenthesis, this means the opposite of 9. That means the opposite of 9. So that's a negative 9. That's right, because over here, this means negative 3 times itself, multiplied twice. Well, now all of a sudden I have a negative times a negative, which gives me a positive. Those are not the same. So when you have an even exponent at the top, be very careful, because this is totally different than that. And you might be thinking, it's just a negative sign difference. What's the big deal? It's just a negative sign. Is it a big deal if you have a positive $1,000 in the bank or a negative $1,000 in the bank? Yeah. I think so. Positive and negatives are a huge difference. So it's not just the negative sign. All right, we are almost done here, guys. Matter of fact, we're going to pause one moment. If we are going, what does the word evaluate mean? What's the root word in evaluate? I'll give you a hint. What? Look over. Okay, to look over, to evaluate something is to look over. Value is the root word. So we are going to give value to, we're going to look over this expression and we're going to give a value to it. How much is it worth? Is it worth 10? Is it worth 15? Is it worth 60? I don't know. Let's see. So if you're given an expression right here with a bunch of x's in it, ooh, but it tells me what x is. So remember how you just take that -2 and I'm going to plug it in wherever I see an x. So I'm going to go -4. In place of that x, I'm going to put in the -2. And I'm going to have to put that in parentheses because I need to square that whole -2. -6 times -2 plus 11. And, ooh, now I need to use my order of operations. So what is that, Sally? What am I going to do first? The squared, right? Exponent? Well, wait a minute. This is the whole -2 squared. So is that a +4 or a -4? It's a positive because it's a negative times itself. It's a negative times negative. So this is -4 times +4. Okay, now I've got some multiplication going on right here. -4 times 4 is going to be a -16. Here's where kids get frustrated. When you look at this right here, remember how you can take a subtraction sign? Remember in, I don't know, when you, probably 6th or 7th grade, a subtraction is the same as adding the opposite. So this is really a -6 times a -2. So that's really a +12. And now this is a plus sign. It's no longer a negative sign because the negative sign went along with the 6. So this is a plus now. And now just do whatever from left to right. -4 plus 11, 8 to 8, 9, 10, nope, 7. I'll do 7. So if you only do one step at a time, and you'll get these easier than if you try to do a bunch of steps at the same time. What does the word simplify mean? Is that to reduce? Yep, to simplify, make it the smallest that you can, make it the easiest that you can. How about like terms?
Same.
The same. There's something about the terms that are the same. So if I say simplify by combining like terms, simplify means to make it simple, and combining like terms mean I'm going to stick like terms together. So if I have 8 x's and I add 3 x's, how many x's do I have? 11 x's. I don't have 11x squared or 11 times 2x or anything like that. 11 x's plus 3 x's, 8 x's plus 3 x's is 11 x's. 5p squared plus p minus 3p plus 2p squared. What are like? What is like the 5p squared? 2p squared. So I'm going to add this p squared and this p squared. 5 of them plus 2 of them would be 7p squareds. And then I've got a p and a -p. How many p's are right here?
1.
Just 1. So 1p, take away 3 p's, gives me a -2 p's. So there's your answer. Now all I've done is simplify. I haven't solved. I haven't evaluated. I've just simplified something with 4 terms. Now it just says 2 terms. Another one under there? Nope. Oh, okay, let's see. We're going to use our order of operations, and we're going to use our laws. So we're first going to need to distribute this bad boy, and we're going to need to distribute this bad boy. Now, I'm going to emphasize to myself that this is a subtraction right here. So I don't take that going with the 4. If this is a subtraction sign, it's going to remain a subtraction sign. So 3 times y is 3y. 3 times 2 is 6. Minus 4 times y is 4y. Oh, but wait a minute. I have to put a parenthesis there because this minus has to go to everything over here. So this is going to be 4y minus 28. Because this is 4 times negative 7. Now, before we go any further, some of you right now are thinking, wait a minute, Ms. McGinnis, that would be a lot easier if you were to take this subtraction sign and do like we did on the last problem. Let's change that to a plus negative, so that this is a negative 4 that we're distributing, and this is a plus. I'm going to show you that what I just did is the same thing. You'll get the same thing both ways. Let's work the top one first. So this would be 3y plus 6. This negative would be distributed to the 4y. This negative would be distributed there, which would make it a positive 28 because it's a negative times a negative. 3y minus 4y would be a negative y. 6 plus 28, what is that, 14, 34. But if I did it the second way, I would have 3y plus 6 plus, this would be a negative 4y. Negative 4 times negative 7 would be a positive 28. And I put them together, 3y minus 4y, 6 plus 28. What do you know? You get the same thing. So whichever of those makes the most sense to you, you can do it either way. Woo! There you go. So there's your first assignment. Again, remember assignments, don't put them on the same sheet as your warm-up. Do them on a separate place in your notebook. You will not hand in your homework, so you don't need to worry about doing this on a clean sheet of paper. You can do it in a spiral. And have fun.